Okay, guys. All right, gang. STAT1800. Going to run through a couple of examples with you. These are some handouts that I've used in previous classes. And I kind of like the way things turn out. And I like the way the questions are posed. To get a copy of this, if you want to play along, which I think is a pretty good idea, let's go to our Blackboard uh, site for this class. And if you go to handouts, and go all the way to the bottom, you'll see ANOVA handout. So if you click that, download it, print it out, you'll get the handout that I'm currently working. Now, going back over, you can see that we have a situation, a problem that deals with pH measures. And to keep us from typing these into StatCrunch, what I've done, I think you'll thank me for this, go to Content, go to Data Sets, and you'll see pH Measures ANOVA. So I'm going to click that. It'll download to my computer. And I can open it up. And you can see that I've got the measurements in terms of columns A, B, C. Now, we've got to be kind of careful with that, and I'll point that out in just a second. So I'm going to save that on my desktop so it's easy to go get. All right, so it's there. Now I'm going to close it down and go back to working the problem. So first of all, enter the data into StatCrunch. So guys, that's what I'm going to do. So I'm going to go to StatCrunch. I'm going to select a file on my computer. I'm going to choose the file on my desktop, and I'm going to choose ANOVA pH. So I'm going to open that. Hopefully it opens correctly. And I'm going to load the file. Yeah, I don't know what else is going on with all these pictures. Well, anyway, I guess we could get fancy, but I don't care about that stuff, so I'm just going to load the file. Now, it turns out that we have ABC. I don't like ANOVA problems set up that way. It'll actually work fine. So what I'm going to do is I'm going to data, and I'm going to arrange, and I am going to stack my data. So I'm going to choose the columns A, B, C, and I'm going to store my labels in, I'm going to call this, what do we have? Soil type. As I promise, I can spell, I just can't. And I want to call these pH measures. So I'm going to compute. And you can see now that I have my measures, and I have two variables, soil type and pH measures, and when I read left to right, I get information relative to one measurement. So I'm going to delete A, B, and C. So let's see, how do I do that? I think I go to Edit, Columns, Delete. So I'll delete A, B, and C. You don't have to if it doesn't bother you. It being there, it's no big deal, but I'm not like that. I like to have it a certain way. All right, let's kind of go a split screen here. So let me get into exit full screen and get this going, and then I'll even get this smaller. Technology is really cool and it works, isn't it? All right, let's go for it. So check the three assumptions. The normality assumption, there's really not a lot you can do. There's something called a Shapiro-Wilks normality test, but I don't teach that anywhere but in my grad classes. So let me get that straight. That's bugging me. So I think what I would first of all look at, I would look at a box plot, and I would look at the pH measures, and I would want to group by soil type. And I would want to use fences to identify outliers. and I will compute. So just kind of making an educated guess here. It looks like to me that there may be significance between A and B and B and C. It looks like A and C will most likely turn out to be equal means, and B will be the one that's not equal. But I don't know that yet. Independence, really independence is part of your experimental design, your data collection. You would just hope that these measurements, you would hope, you have to ensure that these measurements from each of the soil type aren't in some way related. Homogeneity of variance, we'll check that when we run our analysis on StatCrunch. All right, gang, state the null alternative hypothesis. Oh, wow. State the null and alternative hypotheses. So H sub O is going to be that the mu for A is equal to the mu for B, equal to the mu for C. And the alternative, at least one pair is different. At what level of significance should we use? Well, we don't know much about that right now, but I think we should use 0.05. So we should use the 0.05 level of significance. Next thing we want to do is we want to come in and do means and standard deviations and sum. Okay, I don't know why that's there, but it's okay. We can handle that. So I want my pH measures to be grouped by soil type, and it looks like I want the sample size, the mean, the standard deviation, and for some strange reason we want the sum. All right, so sample sizes 5, 9, 12. So guys, what I've done here is I've renamed these as A, B, and C. So these are the technical names for A, B, and C, but I just chose to do it simpler up there. So A, B, and C is again 5, 9, 12. Looks like the sums are 32.2, 50.8, and 73.9. And the means are 6.44, 5.64, and 6.16. So again, it looks like to me that these two means are probably going to end up being non-significant, but it looks like this pair of mean will be significant and this pair of mean will be significant. Don't know that yet. Gotta let the process play out. I know I say that every video, but it's it's something I want to point out. Now, also down here, we want to look at the grand mean. So if I want to do that, I'm just going to calculate the mean for pH measures, but just don't do it by grouping. So 6.03 is the grand mean. All right. You know, technology makes this stuff so much simpler. I've never been a stat geek in a time when there wasn't access to quite a bit of technology. It's much better today than it was. I guess I started my stats career probably around 1997, 98, somewhere in there, and there was some stuff out, but it's really advanced today. All right, so what are the degrees of freedom for the numerator? So guys, degrees of freedom for the numerator are just the number of groups minus 1. So we have, 3 groups, A, B, and C. And then the degrees of freedom for the denominator is the total sample size, which is 26, minus the number of groups, which would give us the degrees of freedom for the denominator of 23. What is your decision? Explain the implication of the studies that relates to the difference in pH measures of the 3 soil types. Well, guys, let's conduct the ANOVA. So I want pH measures. No, actually I've got those in a single column, so I want responses pH measure. The factors are in soil type. I want to compute the post hoc just in case we do have statistical significance. And I want to do a Levene's test of equal variances. Again, that's just a homogeneity of variance, is just a fancy way of saying do we have equal variances. So when I compute this, there's a lot going on. First of all, we have the basic statistics that we've already reported. But next thing I would do is go to Levene's, and we can see that we kind of win the game, meaning we have equal variances if the p-value is greater than alpha. So this is a weird situation where you're kind of seeking an insignificant test. And that's what we have. So we can assume equal variances. So we go to our ANOVA table, and we see that we have a statistically significant result. So the way I would report this is I would report this as F. My degrees of freedom are 5, 9. No, they're not. Where did I come up with that? The degrees of freedom are 223, just as I told you up here. Let's see, I lose my mind sometimes. Then a statistic, F statistic is 5.87. Let me highlight that and show you where the F statistic is. So it's 5.86. And then this p-value would be reported as less than 0.01. Now, guys, I put up a portion of a video, I think in last week's videos, that told us how to report p-values. So our decision is there's at least one pair of means that are different. And since we have a statistically significant ANOVA, we come down and we have that p-value is less than 0.05. That p-value isn't, and that p-value is. So we have B and C that are significant, and A and B are significant. So A and B, the p-value is less than 0.05, and B and C, our p-value, is also reported as less than 0.05. Now the next level of significance would be 0.01, less than 0.01. And again, I went over this in the video before. If you didn't watch it, didn't take good notes, you need to go back and take a look at that again. But this number is not less than 0.01, so they have the same level of significance, even though this p-value is quite a bit lower. So, guys, report the results. That's just really, I don't like the clarity of this thing. Okay, so guys, sum squares. I'm just really going to copy my degrees of freedom to 23 and 25. So my sum of squares is 2.38 and 4.66 and 7.04. Guys, remember, to give mean square, you take this number, divide by 2. Mean square that number divided by 2. And to get your F statistic, you take this number divided by that number. And we could calculate the p-value if we needed to. Those are ugly 8s, aren't they? All right. Sorry about that. All right, next problem. We're getting into, I don't know why this thing is so, just doesn't seem very clear to me. It seems a little bit better. All right, gang, let's open up another file. And, well, guys, I think actually we have to go back here. So let's select another file on the computer. Now, we need to download that, so I'm going to need to go to back to Content and go to Datasets. And the data set we need for this one is rate of removal. So I'm going to just click it, it'll download. And it's going to be by downloads, which, I can go get that. So I'm going to enter, select a file on my computer. And I'm going to go to Downloads. And let's see if I can find this thing. pH measures, right? No, this is rate of removal. Here we go. All right, gang, that doesn't seem to be working. Let me just go ahead and get this and just do a save as. There's no reason that shouldn't have worked, but for some reason it didn't. My motto is always have a backup plan. All right, rate removal, open. Let's choose a picture. This could be interesting. Where would I like to be right now? I would like to be on the beach, scuba diving. Let's choose that. All right, load file. Oh, okay. So we have a picture up there that is completely meaningless. All right. So the removal of, I don't even know how to say that, ammonical. Okay, correct me if I'm wrong. Nitrogen is an important aspect of the treatment of leachate at landfill sites. The rate of removal in percentage per day is recorded for several days for each of the several treatment methods. The results are presented. What can we conclude about the rate of removal? Well, guys, first thing I'd want to do, just as I always do, is I'd want to just take a look at the descriptives. You might say, well, Darbo, you're being kind of redundant. I'm okay with that. So I'd like to go in, I'd like to go mean, I like to go the standard deviation. Let's see what happens. So the waste removal rate for D looks like it is significantly lower. I'd like to follow that up with a graph and do a box plot. So do rate, and I'm going to group by treatment. Use fences to see if there are any outliers. And again, I look at these lines, and they're pretty much on the same vertical line, aren't they? But this one does it. Now, I have some concerns about equal variances here, because when I look at the distance from the top to the bottom of A and the top to the bottom of C, I don't see a lot of difference, but I sure do see a lot of difference between A and C and D in variation. So there's a good chance that we might run into a situation here where Levine's test is significant, which tells us we don't have equal variances. So guys, I'm going to go ahead and run the ANOVA. So I want to compute Tukey just in case we do have significant difference and I need to test homogeneity of variance. All right, so let's go. First thing I'm going to look at is the equal variance for Levine's, and it turns out, and the reason we probably couldn't reject it, didn't get a p-value less than 0.05, is because we have such a small sample size, only 4 measurements in each treatment. But nevertheless, we can assume equal variances because the p-value is not less than 0.05. However, when we go to our p-value here for the ANOVA, we see that our p-value is greater than 0.05, so we can't assume any statistical significance. So essentially what we do, we fail to reject the null, which says that we can't reject the statement that the mean rate of removal for treatments A, B, C, and D are different. So, for something like this, I would report F, and our degrees of freedom look like they're 312. And the test statistic is 2.15. And our p-value is 0.147. So there's no need to do a post hoc because our ANOVA isn't significant. So guys, you can't if this was part of something that you were doing for your job, and you really were concerned about this, there would be no reason to suspect that there's a difference in rate of removal across treatment. However, you can't help, even though it's not significant. You can't help but look into your sample data and see that the rate of removal for C and B and even A are quite a bit higher for these four measurements, but you can't generalize it to the population. So I think what I would do if I were a statistician with this, I would want a large sample size, maybe bump up the number of days that we measure address the rate of removal, maybe go up to maybe 30 days for each treatment. And I think if we did, I think you'd probably end up seeing significant difference especially between C and D. All right, gang, that's all I got. There's going to be one more video that I'm going to put up on ANOVA, and that's going to be working some problems on my math lab, or my stat lab, whatever you call it. So, guys, take care.